Uh, Thank you, everyone, and thanks, Luke, for the invitation. My presentation is not as fancy as the first one, so my apologies. And also because I'm a mechanician, it's going to be probably a little bit boring in the beginning. Just bear with me for 2 or 3 slides, and then I promise no more formulas, only pictures. And my goal today is, in the end, is, because as 446 fracture mechanics, we've been seen for many years as the boring formula guys who do things in their own office, but they don't have any practical application. My goal today is to show you that what we do actually has a very important application, which is size effect. And we design, but we don't know that actually larger structures do not behave as small structures and what you test in your lab, like the modulus of rupture. And also, this is particularly important when you don't have reinforcement for concrete or when you have a small amount of reinforcement. But this applies to other materials. Just an example, bones, your bones, they will fracture at a different stress if they are the larger bones or they are the small bones, because it applies to a lot of materials. So I'll give you again, the first bullet is my 2 minutes of boring stuff, okay? And then I'll try to explain you why concrete has this particular behavior with size effect. And I'll show you the test that we have been doing in at Case Western, which is the largest ever set of tests in the world being attempted. And then I'll give you a couple of quick notes about modeling. And the reason is Luke asked me about what if a large slab has a fixed end and we have a different behavior, or what if it's not just a 1-point crack. So I'll just give you a couple of ideas of what we can do. And then conclusion, and I'll try to show you what really we don't know yet and what we really need to research on. So just to start a little bit light. So in fracture mechanics, it depends how your crack opens, right? So we want to focus on the first one on the left, when basically your crack opens perpendicular to the line of the crack, because this is really what happens most of the times in flexural cracks, but also, in shear, flexural shear cracks, that's actually what happens. So it all started really recently. So fracture mechanics is not as old as strength of materials, okay? But the main point is this one. And again, this is probably just the boring part. So it was realized in the 60s, 50s, that when you have a crack near the tip of the crack, your stress is much higher than far away from the crack. So in other words, there is a stress concentration. You have the same stress concentration in holes when you do your gusset plates for trusses, okay? But when you have not a hole, a circular hole, but a crack, this stress concentration is really high. So when I teach my student this part, I say, well, if you learn a strength of material, there is something that doesn't, fit the whole, statement, because that would mean that near the tip, even if you apply a very small tension, you will have the crack propagate. So what we learn in strength of material as engineers does not apply whenever there is a crack. And I'm not saying, you have to see a large crack. You can see a defect, something that is embedded in your material, okay? So the stress near that tip, it goes this way. There is a term on top, and then at the bottom, there is the distance from the tip of the crack. So of course, if R is the distance and R becomes very small, the stress goes up. But the terms on top, K1, does not. And that's what we're really focusing on, the stress intensity factor. So the stress intensity factor for whatever geometry you have has always this sort of structure. The stress that you apply, and then the square root of the dimension that it's important in that structure, in this case could be the width of the plate. And then a term that depends on the geometry, K alpha. So if you were a student, an engineer in aeronautics in the 70s and 80s, there were these gigantic books of fracture mechanics with that K alpha for all the geometry. So when they had the rivets on the wings of the plane, they were looking for the crack near the rivets, what was the K alpha, and they were designing to make sure that that crack did not propagate during the fatigue of the wings, okay? And when the crack propagates, the term on top, K1, becomes a critical value that is a material property. You can test it. There are ASTM standards for that. And the stress became the peak stress of your your material can take. And that K1C, that material property, is called the fracture toughness in fracture mechanics. I'm almost done with all the difficult part. Okay, so my apologies for the non-engineer audience. So I'm going to take a break and I'm going to tell you what happens in concrete, because in concrete something different happens. Okay, so it was realized in the 70s that if you take a piece of concrete and you pull it in tension, before the 70s, the machines were not capable to run a test in a stable manner to see what happened after you reach the peak. And so they were saying, oh, concrete is brittle. So if you ask most engineers who are not probably from, recent years, and even some still, they say that concrete is brittle. Well, concrete is not exactly brittle, because if you do the test properly, after you reach the crack, let me see if there is a point. I guess I can use this one. Yeah, my bad, so that they can see it also. So after you reach a crack, you can continue to pull. And what is going to happen is that as you pull more and more, your stress decreases, so you can carry more, but you can still carry an opening that crack. And why is that happening? Because there are aggregates that they cross the crack, because the crack is not flat, there is friction between the surfaces, because there are voids and the crack needs to go around. So for a lot of phenomena, in reality, there is life after the peak. And we call that, the softening behavior of concrete. So the way to model that is very simple. You say concrete is going to go linear up to the tensile strength, F prime T, and then it's going to have a softening part, okay? And the softening part will give you basically, how much the concrete can open before really there is a physical separation between the two faces of the crack. And it's pretty simple to model that. And the ingredient is, again, that softening part, okay? So that basically opening of the crack as you can still transfer some stress. And by the way, materials like fiber reinforced concrete, they still behave the same way. And initially they behave exactly with the same softening curve. Then they have this long tail because the fibers, of course, will restrain that opening and they let you open more and more. Now, I was listening to the presentation before, very interesting. And I actually had a thought. When you're looking at these values of the opening, you don't have to expect that when you see a real crack. That's too late, okay? We're talking about less than a millimeter, sometimes a third of a millimeter. So you don't see the crack when, you are at the end of this opening with stresses, but the crack is there, okay? So you need to use, if you use alcohol and you spray alcohol on the surface of concrete, you will see the crack, but you cannot see it with your eyes, but the crack is there already. And again, the area under the curve is something that we use to quantify, the quality of this crack opening, which is the fracture energy. So why am I saying all this? Because if you remember that picture of the stress getting really high near the tip, now you have a problem. The stress will never get high near the tip because you will have the softening. So basically what you have is that the stress goes high far from the tip. And then you have all this softening part near the tip. And we call this part here basically the fracture process zone. And for concrete, that fracture process zone, that area where there is softening, is a function of the aggregate size. So you have a very large aggregate size as the maximum aggregate. That softening can be in the range of feet. You have a fine grain, that softening can be in the range of inches. Just to give you an example, graphite Okay, it's considered a brittle material. But graphite has a fine grain in the microscale. So if you tested the microscale, you will see the softening. If you tested the large scale, the softening is so tiny that you don't see it. Okay. So for example, to go back to the practice, concrete. If I have a concrete with small aggregate or a high, UHPC where they use fine aggregates, that softening is pretty small in size. But if you use large aggregates, okay, that softening is gigantic, okay? And this is, if you want to summarize what happens in fracture mechanics. When the fine grain is there, you can apply the idea of back the engineers in the 70s. There is stress concentration near the tip on the left. If your material is a metal, forget about all I said, because then you have plasticity and there is a large zone of plasticity near the tip. If your material is concrete, ceramics, composites, rocks, okay, that they have a grain, then you have all that softening, and that softening can be very large. I'm going to show you that softening later on in a slide. So I'm done with I think all the formula except for one, which is the only one you need to remember, okay? So what is the problem? We all know that there is size effect in concrete. So we know that if you have a structure that is really large, the stress at which that structure fails is much less than the stress at which a small structure made of the same material will fail. We all know that. In fact, I'll show you ACI 318 has incorporated that, okay? What is the problem? It's not easy to understand really the details because there were tests done in the past, but they were only using 3 sizes. Then there were tests done, not always being careful about certain details, as I will show you. So it's really hard to compile data without, risking that the scatter leads us to something different. But I want to make a point. If your material was like the first one, very small, fine aggregate that you basically cannot see, so that stress concentration applies, the size effect will go as 1 over the square root of the dimension. You see it here. And the reason is very simple. If you remember the formula that I showed you, if you solve for sigma n, the stress, you get that it goes as 1 over the square root of d. So basically, your stress decreases at failure as 1 over the square root of your dimension. Okay, so as you can see, it's a pretty significant size effect. This is the strongest size effect you can possibly see. You see it again in those materials like graphite that has a very fine grain, and the stress concentration can be applied. So let's go to concrete. What happens to concrete? These are the 2 graphs that you need to take away to learn basically a little bit size effect. So if you plot in a logarithmic scale, just because of, the sizes can get big, the size of your structure, log D, and the log of the stress at peak, okay, of your test, you will see that size effect is basically this solid line here. Okay, and as you can see, as the structure gets really large, it goes down as the square root of 1 over d, which is the case of stress concentration. Because when your structure is, 10 feet, that softening is very small compared to your structure, and you can consider there is a stress concentration. Why you see 2 graphs? So the one on the left is the one we care most for some application, is anytime you have a crack that will propagate until you fail the structure. The one on the right is when your crack will start propagating immediately and there will be no basically stable propagation. So the one on the left is concrete notched beams, compression of cylinders. The one on the right will be your modulus of rupture, okay? So they go down basically almost the same way, except that one will continue to go down and the other at some point will kind of, slow down a little bit on the slope. But I can guarantee you that all structure will have size effect if they are made of concrete. And the one on the left basically follows these very simple equations. So the stress at peak will follow basically a constant on top, and it will go as the square root of 1 plus a term with the size. So I want to show you an example of that. So for many years, 30 years, the ACI 318 committee was told that there was size effect for VC, the shear strength of concrete, plain concrete, okay? And what you see here are all the data available up to 2016 of shear failures of reinforced and not reinforced concrete beams, okay? And you see them here not in the log-log plot, but if you plot them in the log-log plot, it will be exactly the graph that I showed you before. And if you look at the current ACI text, it would say that the VC should be calculated with this formula. So this is the axial force. So if there is no axial force, of course, you don't count that. And this is what you're familiar with, 2 square root F prime C BWD. The only difference is that coefficient lambda, which has this shape. And if you look carefully, is exactly the size effect, okay? So currently, since 2019, there is size effect accounted for in the design of shear strength of concrete. This was, I think, my only great achievement during my chairship of 446, because I convinced them that it was necessary to have that, okay? So we decided to attempt something a little bit difficult, and we said, okay, well, let's try to do the largest ever set of tests to prove that size effect is really that way. So we cast basically 5 sizes of beams, of concrete beams, with basically multiple of the depth. So we went from 3 inches, 75 millimeters, to 1,000 millimeter, which is basically 40 inches, okay? And the span was 3 times, the net span was 3 times the depth. So basically, fairly large beams. This is all the casting. We basically occupied the entire lab for a month. So my chair was very happy about it. And, we did all the casting, very careful about making sure that the concrete was always covered with water. And we also cast a large amount of concrete cylinders, because what we wanted to do, we didn't want to test concrete right away. We wanted to let it, mature enough that we were sure that concrete was kind of stable in terms of strength. The reason being that this test, especially the large one, requires each of them a day or 2 just to set up the test. So of course, if you start to put together all the tests that we did, we didn't want to spend the test in 2 months, and the concrete was still young enough that in 2 months there was a difference in the strength. So as you can see, we waited. This is the tensile strength and the compressive strength over time. We waited that there was a kind of a plateau in the strength, so that we were sure that the concrete was kind of, at that point, sure, still, maturing, but at a very, very low pace. We also measured the elastic modulus over time. We checked the density, all the specimens, all the cylinders were weighted to make sure that, the specific weight was constant. And then we had to come up with different setups for the different sizes. So my student, played a little bit with finite elements, and we design a fixture that was rigid enough so that there was no movement of the fixture during the testing. And we had one for the first 2 sizes, the 3 and 6 inch depth. Then we had a larger one for the third size, which was 10 inch depth. And then we had the problem of the fourth and the fifth size, because the fifth size, again, a 40-inch deep beam, 160 inches long, because you need a little bit of extra, length after the support, was a little bit different. So we did something new, I think. I mean, at least I've never seen it before. So we tested them horizontally. We put them on a bed of plexiglass balls to make them float. And basically, if you look at this picture here, or this one here, this is my student with a harness hanging from the ceiling taking the pictures, basically. So the beam is on the floor. You can see here, lifting the beams. And you can see the plexiglass balls. We bought, I think, roughly 1,000 different plexiglass balls until we found one with a very, very small tolerance so that they were rolling perfectly and they could take the load of the concrete. Okay. The large specimens were about 4,000 pounds. Okay. So a little bit of weight on the plexiglass ball. And then we said, wait a second, somebody's going to raise his or her hand and say, are you sure that the horizontal test is the same as the vertical test? So for the fourth size, we also tested vertically. As you can see, it's a little bit of work because you need to strap it, making sure that it's safe. And so we, as you will see the results, yeah, they were matching. So the horizontal test and the vertical test was actually a match. So we had to do a little bit of work. All these beams were notched. So basically there was a notch of a quarter of the depth. And we did all the tests in roughly 2 months. Basically that happened starting a year after the casting of the concrete, exactly during the beginning of the pandemic. So basically one of us was going in, spraying everything with the Lysol. The other one was coming in. So it was a little bit of a challenge. When we ran the test, we did check a couple of things. One, that the crack was not going sideways. Sometimes it does happen. There might be micro defects, and we wanted to make sure that the data were consistent. And also another thing that we checked is that when the fracture of the surface was all possible, open, the concrete was still wet. And we disregarded those specimens that were dry. If you test concrete and your concrete is in full moisture condition, it will have a strength lower than a dry specimen because of the water in the pores. So you might say, well, in the field, there's no water in the pore. Yes, you're right. But here we are trying to get consistent data so that we understand the trend. So you cannot have basically data that, some are dry, some are not. So we disregarded everything that was dry. And in fact, one of the large specimen was dry. The reason being that the first time for the first test, it took a little bit of extra time and my student forgot to wrap the specimens with plastic and burlap as we were proceeding to prepare the specimen. So we removed those specimens from our analysis, of course. These are the results in terms of load versus the opening of the crack, which is how we control the test so that we can look at the stable opening of the crack. So they are very consistent. And if you want, this guy in yellow is the fifth size, the largest one. And as you can see, it's the dry one with a higher load, okay? And we saw that in all the other tests. Every time you see a peak that is different from the other is a dry specimen, okay? We did also a little bit, we wanted to be a little bit on the sure side that everything was done properly. So there is a formula that allows you from the first part of the response to back calculate the elastic modulus. Okay, so we wanted to say, we want to make sure that all the tests, horizontal and vertical, they are still consistent. And this is the elastic modulus calculated from the initial linear part of the response. As you can see, we are, in the 30s gigapascal. And these are the results from the compression of the cylinder. So we were sure that, our test was done properly. These are the responses in terms of load versus the deflection, okay? And you see a snapback in the larger specimen because of the energy release. This is, just for us who want to play with the fancy formulas. But I also want to point out something else. Don't mind the numbers per se, because this again is the fracture energy, that area under the softening part. But I want to point out one thing. You see different numbers here. What is interesting that if you test your very same concrete with a rate that is 20 times the rate of testing of the other specimens, you get a higher load at the peak. So the rate of the testing is very important. That's why it's so hard to take data from the literature, because if you start to pull in data and you don't know when they were, if they were tested with a certain rate, especially old data, when there was not that habit of reporting all the details of the test, even for compression, if you test your cylinders at a higher rate, you get a higher strength. So the strength increases if you increase the rate, okay? So all things to keep in mind if you really want to compare data. And then we did something else. We really wanted to see that softening. We really wanted to see what was going on near the tip. So we use a technique that is called digital image correlation. Nowadays, a lot of researchers use it. I started to use it in 2004. It's a very simple technique. You spray your surface with dots, random dots, with a base of white, and you use two cameras to take pictures as you do your test. The software is able to correlate where those dots move, and they will give you the deformation of the entire surface. So this is, for example, you see from top the large specimens. And that's why we had that problem with the dry specimen, because for the first specimen, my student took 2 days to manually do all the dots on the large specimen. And unfortunately, didn't think about covering the specimen. So we had to create basically an environment to continue to do the dots without losing moisture. So, you learn, it's the first time we did that. But what I want to show you here is what we saw. So we capped the profile of the deformation in the horizontal direction to the tensile, to the strain corresponding to the tensile strain. And you can see the fracture process zone, that zone where there is softening. So anything inside the yellow bulb is where you have your softening. And you can see how for different values of the load, as you go up and you go down, okay, you see basically this fracture process zone developing. We also looked at, to measure this fracture process zone. And because we had, all this information from the IC, just I want to show you a quick interesting thing. If you take a small area next to the crack and you measure how much they move with this image, digital image correlation, you can see in these curves the opening of the cracks. So you can see how much they open. So you can actually measure how much they open, and you can use that. But I think the most important graph that we want to look at is this one. This is the size effect. So this is the stress at peak for the 5 sizes, okay, in a log-log scale, which is exactly, the size effect law that I showed you. Okay. So if you don't have the log-log plot, you have a stress reduction that could be in the range of 50%. Okay, between the large and the small size. So let's say that you test a concrete instead of this one with an aggregate that is, I don't know, 1.5 inches. These very same beams, they would have been all farther up. Okay, so you would have been farther up rather than getting close to a very, strong size effect. If you were to test beams, same sizes, with a very fine aggregate, they would have been all the way down. Okay, so where they are in this trend depends on your aggregate size. Okay. Okay, so how to model this? Well, you can model, there are softwares of different types, discrete particle models. You can use cohesive laws in a, discrete element. But I want to show you one thing that I thought was interesting, very simple, but really useful to use it also in design, I think. It's not for everyday design, but if you're looking for a particular large structure with certain constraint, that could be a way. It's called the cohesive hinge. It's something that was used for fiber reinforced concrete in the last 15 years, and we try to use it just for plain concrete. The idea is that you basically imagine that in the central part where you have that bulb of that you saw the cohesive material, there is a hinge. Like if you're familiar with steel structure, it would be similar to your plastic hinge, okay? But the difference is that as this hinge rotates, okay, it basically doesn't have the same moment, but it decreases the moment because you have the propagation of this cohesive part, okay? So it's a rotational hinge with a certain capability of transferring load, but it changes as you increase the rotation, whereas the plastic hinge always gives you the plastic moment, right? So you don't change the moment. And you don't know the parameters of this hinge, but what you do is, with a little bit of MATLAB coding, you can basically obtain those parameters of your softening by matching the experimental result. And once you have it for that concrete, then you can use it to model. So we use it to check the experimental data. They were working very well. We tried different methodologies for the cohesive hinge, and they were working very well. But I think the goal was in the end to say, okay, if I have now a structure that has constraint at the end, so this crack can form first at the ends and then in the middle, how can I model that? Well, you just need to put 3 hinges. The first 2 that will activate are the one at the ends. And then as these start to rotate, they will release load because of the propagation of the crack, and you will start to open the one in the middle. So this could be, if you want, if you're familiar with design of steel structure, the equivalent, but the hinge is not exactly plastic, it's cohesive. Very simple. Again, once you calibrate it for a certain concrete, and you can calibrate it for different concrete quite easily, you can then basically work on the modeling of your structure. So I'm going to spend a little bit of time on the conclusion and actually on the future, because that's what I think the discussion could be interesting for 380 and people who are here. So in conclusion, fracture mechanics really can be used to predict size effect because there is a crack that propagates. And in concrete, this crack is a softening instead of being, just a point. You can use fracture mechanics and the size effect data to actually predict the properties of this propagation. You can really get a powerful tool from DIC to model the softening. And, the data confirms it. It does confirm, the data confirm that there is size effect in concrete. And actually in plain concrete is the worst case, or where you have a light reinforcement. The more you have reinforcement, the more you mitigate your size effect. The less reinforcement you have, and then you go to plain, the more you have size effect, okay? And the cohesive hinge model can be easily calibrated and used to model different structure of very complexity. So I think that, just take away to discuss a little bit of, future in this area. So I think one thing that would be nice to do is to go even now that we know that we can test horizontally, it would be nice to go even one farther size up, like, and do 80 inch deep. So to make sure that really we get that. Also, this can be used for shear. So you can easily do a test where, you change how the supports are, and you can do the shear test and have a set of data to also see the VC of concrete. Another thing that I think is important is really we need to do this test for at least 3 different types of concrete to really get a sense of, the importance of the aggregate size. And I want to add something. If you use fly ash, this is going to be even worse because we did some tests I'm not showing today, but fly ash, the one that doesn't react, the unreacted fly ash, is a very, very easy path for the propagation because fly ash is spherical and it's a perfect sphere, and your crack will not go around the aggregates, will easily go through the sphere very easily. So whenever you use cementitious materials, this size effect can be even more pronounced. So I think this is really where we're looking to understand more. And once we know this, then modeling is very simple, I think. And with that, I'm going to thank you. And this is my student on top of the 5 sizes. Thank you.
So do we have any questions for Christian? Yes, sir.
Professor Carloni, actually very good presentation. I have 2 questions very fast. The first one is, as you mentioned in the technical literature, it's hard to compare the values, right? Because we don't have a lot of information. But is it possible that in the case of UHPC, we might have, instead of decreasing the shear capacity as the size increases, can we have some different trend that increases the shear capacity? And the second question is, do you think, I know that size effect is related to the aggregate size. However, in UHPC, we don't have aggregate size. We have only maybe less than 8 millimeter aggregate size. Do you think there might be any fiber interlocking action that can generate this or compensate this effect? Thank you.
Yeah, very interesting question and very appropriate. Yeah. So what I can tell you is this. Yes, the aggregate. I'm going to start with the second one. Okay. So there are tests. It has been shown that there is size effect for UHPC. The question is, if your crack is opening, the fibers will stop or delay the opening, but the initial cracking is concrete because as to crack the fibers, they need to open so the initial crack is concrete. So that's why there is still size effect. And so actually you will have even farther. So if you look at the data, they will be even farther down that curve because your aggregate size is very small. Now in shear, it's actually tricky. And I don't think there is enough data because now you have a crack where there is a lot of interlocking and the fiber might play a role. So in the shear, I honestly don't know. I'm not aware of data that would say yes or no, but in flexure, I can tell you there is size effect.
So are you basically saying in fibers that the modulus of rupture, since we're talking about flexure, will basically not increase in the presence of fibers?
The modulus of rupture.
That's what you were basically just saying.
Right. So if for the test I've seen, if the cracking it's usually due to concrete. And so if it's due to concrete, then the fiber can play any role. The fiber cannot play a role.